Batteries, I guess, grew in a similar direction that I have grown and thought I had done it just sort of organically. But maybe I was watching Sanjoy. And what I mean by this is that so Professor Banerjee is currently a distinguished professor of chemical engineering at the City College of New York. And he also leads the Energy Institute at CCNY, which most of you know that's what I also do here at Cornell. He started his scientific career way back, but I think the part that I know the best is Santa Barbara University, University of California, Santa Barbara, many years ago decided to hire him to head their chemical engineering department. And he promptly not just made it one of the best in the country, but did it by essentially denuding Caltech of all of their superstars, which is a very interesting approach. But he is still remembered for the legacy of competence and scientific rigor that he endowed in that faculty. Now, Sanjoy is going to talk to us today about work that he has done as part of a spin-off, I think, that started with technology developed in the Energy Institute at CUNY that has to do with zinc manganese oxide battery technology. And he's had the kind of unique perspective of seeing this technology all the way from the anode, dendrites, to figuring out a cathode for that anode, the great anodes, and ultimately to doing it at scale in a company that is now selling a product. If you look at his track record, in particular his publications, you will see that it has nothing to do with any of this. That he essentially made his mark analyzing theoretically high Reynolds number flows of fluids, in particular fluids that have microphase structure. So it's indeed quite an honor to have someone with this background and this perspective teach us something about energy storage materials. Sanjoy?
Thank you, Lyndon. Thank you. It's a great pleasure to be here at Cornell. I think the last time I was here was almost 10 years ago, and it was actually Steve Pope who had invited me to talk about turbulence. Right, so it was a very different topic at that time. In any case, about 10 years, about 9 years ago, I moved from Santa Barbara to City College, and even at Santa Barbara, we'd been interested in looking at electrodeposition problems, and one of the substances we were interested in was zinc, which was a terribly complicated problem because it tended to form dendrites and structures which were very complex. And the way we got into this really was because these could yield to some approaches like phase field models, and we were trying to apply these. Now, it's a long journey from that to what I'm going to talk about today, but in any case, let me start. So let's see if this works. Oh, this is
one on the right.
Right? Okay. Okay, so the first thing I wanted to and this is fairly obvious to all of you, but I nonetheless thought it would be useful to give you an idea of why things like batteries are important. And one of the areas that we are particularly interested in is in applications of these energy storage systems to problems related to the grid, not so much to transportation, though that could also be an important application. So as we get more, let's say, resources like wind or solar into the grid, like here, these, as you know, are intermittent resources. They're not available all the time. So if you put energy from these resources into the grid, it can be out of phase with when you actually use the resources. So ultimately, as larger fractions of the grid become renewable, which I think will happen at least slowly over the future, we need storage systems in order to be able to supply energy, as you know, when it's needed. And there are many other applications, and one of the applications you'll see is that as more and more renewables come into the grid, as climate change affects severe storms and fires and things like that, there is also the need for some storage in the grid in order to be able to back up, critical infrastructure and things like that. Okay, so this just places this in the context of what the needs are. I want to show you very, very briefly one of the ways we store energy for the grid and which is batteries. And this is a very simple idea of a battery. But what you have in a battery is a system where some sort of a redox reaction goes on in the anodes and cathodes, which produce or take up electrons. Ions are transported through an electrolyte. Perhaps there's a separator there between the anode and the cathode. So here only ions get transported and electrons get transported that way. And typically a battery consists of a current collector, which collects the electrons, and an electrolyte, which transmits the ions between the anodes and the cathodes. And typically there are reactions which occur which release electrons or take up electrons. And this is a way that energy is stored. So when you charge the battery, you effectively bring the anode and cathode to a state which, when discharged, would release electrons or take up electrons. Okay, so this is the basic idea. Now, one of the attributes of various materials is that they can store energy electrochemically. So zinc, for example, if you make it zinc oxide in a electrochemical reaction, can release energy. And to give you an idea of how much, if you took a cube of zinc about 18 meters in size, which is pretty large, yeah, it's a big cube. It's a very big cube, but it could store the energy of Niagara Falls for 1 day. Okay, to give you just a scale. Okay, and if you did the same thing with lithium, you would need roughly 2 cubes, and similarly with lead. So all these metals, if you use their theoretical energy storage capability, would give you this type of energy storage, and you need a lot of cubes, of course, to store Niagara Falls. But nonetheless, there's a lot of zinc around, and actually if some of you went and looked at a zinc plant, it covers acres electrochemically, and they have these huge cells, and they dissolve the zinc, and then they electrodeposit it in big sheets, and they take it off, and that's what we use. And they dam a river, like the Fraser River or something, and that's how they electrochemically produce the zinc. Okay, so it is an effective energy storage medium. Not as good as a nuclear reactor, of course, but it's some approximation. Okay. Now, if I look at it again from a slightly different perspective, why is zinc so attractive as a material to store energy? Of course, aluminum is too, but I'm just talking about zinc. Is that that the Niagara Falls for a day can be stored in this cube, which can be reused, of course, but the initial cost of this is about $100 million. Compared to if I had to do it with lithium or lead, this is typically the theoretical amount at current prices that would be needed to do it. So that's one of the reasons it makes it attractive. And also if you look at, say, the greenhouse gas emissions, which are involved in making a battery with zinc plus something else is needed. In this case, I'm talking about manganese dioxide. So this gives you an idea, and this is sort of a zinc plant, manufacturing. If you look at it, hundreds and hundreds of electrodes, huge in size. So this is where it comes from. Now, there are many reasons why zinc has not been used so widely. We can go into this as time goes on, but I'm going to give you this as a background as to how we got into this. It's an attractive medium. There are issues. Because it's attractive, it has been used or tried to be used in the past. So there's many zinc chemistries. Zinc itself is the anode. You need to have a cathode of some sort. And in the case of zinc, one of the most useful cathodes is actually silver. And the zinc silver batteries are very high energy density and are widely used mainly for weapons systems, things like torpedoes and in submarines and so on. They're expensive, and therefore it is a sort of a specialized use. The other zinc systems which have been looked at are zinc nickel. These are nickel really oxyhydroxide. So the oxyhydroxide and zinc pair, and when it discharges, it becomes nickel hydroxide and zinc oxide. And those are batteries which are used not very commonly, but it's becoming more and more exploited now for some specialized uses. Nickel is quite expensive, and therefore it's not easily a grid storage system. But it has very nice characteristics in many other ways. Zinc air batteries are also used, and like lithium air, these are very difficult to make rechargeable. Nonetheless, they are used very widely as primary batteries. So for watches, hearing aids, and then there are some large ones which are made by a Spanish company called Segesa, which are used for things like railway signal lights and all sorts of other things like that. So rather specialized uses. Zinc bromine is a rechargeable battery which is has been developed to some extent. These are usually what are called flow batteries. They haven't found widespread use, but there are some attractive features. What I'm going to talk about more is zinc manganese dioxide. Manganese dioxide is a very common material, very inexpensive, and most of the non-rechargeable batteries that you use today are zinc manganese dioxide. These are your AA's, your AAA's, the Duracells, the Energizers. They're all primary zinc manganese dioxide batteries. Alkaline batteries, they really are a single use, and the reason for this is when you discharge them, the manganese dioxide goes into an inactive species, which I'll talk to you about as we go on, and it's not easily reversible, so it can't be recharged. And part of the problem with why zinc and manganese dioxide are not more widely used as rechargeable batteries is this formation of inactive species when it is discharged, which tends to block the possibility of recharging it and discharging it again. And so it is essentially been a single-use battery. So the discussion that we are going to have today is how we were able to make this pair, zinc and manganese dioxide, rechargeable, and then how we are going about trying to make it into a commercial product which can be widely used in the grid for supporting renewables perhaps, or backing up critical infrastructure and so on. Okay? Now, the main thing that's interesting about zinc manganese dioxide is the supply chains for all the materials here are already well established, because they are already a vast industry, the primary batteries. So I don't know what the number is, but at least 30 or 40% by volume in terms of sales of batteries are these primary batteries sold by people like Duracell, Energizer, previously Eveready, Gold Peak, who knows, I mean, hundreds of companies all over the world. So it's a vast business already with a very well developed supply chain. So you don't have to develop a supply chain for the materials that go into these batteries. Not, some maybe, but not all of them. Okay, so let me go back now and show you from a broad view how this developed in some ways at the Energy Institute. About 9 years ago, as I told you, I moved there. There were ideas about using zinc, which had arisen because of interest in dendrites. But then over this period of time, we went in many different directions and, as usual, pivoted here and there, but I'll give you an overview of this. So let's say early phases, around 2008 to 2010, right up there, we formed the Energy Institute. It happened in ways which I'll tell you the story later, but Andy Grove, who was a City College graduate, had a big hand in this, in getting this going. And he had his own ideas about what the mission should be. And the mission was to try to, not have the US so dependent on foreign energy resources. So, I mean, that was really the way he looked at things. And part of it was he wanted, he used to call sticky technology. So he liked renewables because it had to be used more or less where it was generated or close to, okay? So that was part of it, but part of the other thing was, of course, there's a significant nuclear program that had to start as well, and plus some enhanced oil recovery. So all this came under the Energy Institute, but the part I'm going to talk about is the energy storage. So when we started with an interest in zinc, which was historical, and we looked at both anodes and cathodes. So I've sort of divided this in two parts. We started originally with what I'd call flow-assisted zinc, and the reason for this was the first way we started to think of trying to control these dendritic structures and things that occur in zinc was by having a little bit of convection, either self-generated or actually impressed. So this whole area of flow-assisted zinc, which went on and actually got built into significant systems, fairly large ones, persisted over the next significant length of time. Till 2014, we were building fairly large systems, 1 kilowatt-hour batteries, stacking them into 30 batteries, making 30 kilowatt-hours, and doing experiments which were fairly significant in scale. But we also started to look at zinc as, let's say, metal or pasted, more in solid form. And you had to do certain things to it in order to prevent it from passivating, from forming dendrites or moving all over the place. So there's all sorts of problems that occurred with it. And there were some clever things that had to be done to keep the zinc still while it went, formed oxide and electrodeposited back and forth. So there's a whole line of work that started with pasted zinc. And at the same time, we started to look at different cathodes. And the early cathodes we tried were nickel. And these were beautiful cathodes. Even today, they will last forever. You can cycle them, and they have all sorts of beautiful attributes. Sintered nickel, nothing to beat it. These are the cathodes that you have in your hybrid cars, you know, the nickel metal hydride. They last forever. The only problem is they're very expensive. Okay, so while you can certainly use them for transportation and other things, they're not ideal for large-scale application in the grid. Okay. And we also started to look at manganese dioxide. Manganese dioxide, as I said, is a very difficult material because it has many polymorphs in its crystalline form, and if you discharge it, it tends to form inactive species. So you have to be, find new ways to make this happen. So one way is to keep it in a certain crystalline state during charge and discharge, which avoids some of these problems by what I'd call shallow cycling it. In other words, there is a 2-electron discharge reaction. The first electron part of it is really a proton insertion part, which maintains the crystal structure. It can be destroyed if it's cycled too many times, but it is able to be cycled within a shallow region without actually transitioning the crystal structure to something inactive. And then there's a second electron region, which I'll talk about, where there's a conversion reaction actually, which changes everything. So manganese dioxide goes eventually to MnOH twice, and this is a completely different crystal structure, has a completely different material, goes through a solution precipitation thing. So if you have to bring it back, it's very difficult. It has to be retemplated and recrystallized. And so the second electron region is a particularly difficult deep cycle manganese dioxide to make that happen. So all this was funded by DOE and NYSERDA and so on, and in particular by ARPA-E. There were a couple of ARPA-E grants, mainly for grid storage, which led to these developments ultimately of this deep cycled manganese dioxide, which I'll talk about. You need certain dopants to stabilize the crystal structures, retemplate it, and we can go through that in detail. But in any case, about 2013, actually as part of the ARPA-E grant, we spun off a company called Urban Electric Power. Initially, it was about 10 blocks from the campus, but now it's like 30 or 40 miles away because it needed more space. And the Urban Electric Power, as you'll see, started to apply some of this technology that was developed, particularly with the pasted zinc and the manganese dioxide. It initially also did some flow-assisted zinc and nickel, but it was too expensive to be commercialized really on large scale. And currently, Urban Electric Power is starting to deploy these systems particularly for backup applications. I'll show you these. And there's a pilot plant operating. So the pilot plant is not such a small pilot plant actually, because it produces a few megawatt hours of storage, but it's about 30 miles from New York. Okay, so there are other little things that I've shown you here, but really where we are going is to get to these deep cycle technology that is coming into Urban Electric Power. Okay, so very quickly, let me move on. Zinc manganese dioxide batteries. I'm going to just briefly tell you about these. They started off as primary batteries. They're very, very inexpensive, about $18 to $25 a kilowatt hour, way below any other battery. Of course, they're not rechargeable. So what you have to do is to try to make it rechargeable. They have a very low cost of materials, low manufacturing costs, and there are various other things which are of interest. One particular thing of interest is that they are very easy either to recycle, or if you wish, you can even dispose of them. You can eat manganese dioxide. It doesn't do too much harm. I don't know what happens if you eat too much zinc, but I believe in small quantities, it's okay. Right? It actually gives you something for your immune system. All right? So the ultimate challenge is reversibility. So let me give you a brief history. Zinc manganese dioxide started with Leclanche. Back in 1866, he made the Leclanche cell. This was actually zinc carbon manganese dioxide. And then nothing much happened till Urey, he was a Canadian. This was in the 50s, came along, and he made the first alkaline zinc manganese dioxide battery. Shortly after that, there was Carl Kordesh, who was at Union Carbide, and he made a slightly rechargeable zinc manganese dioxide battery, which was never really exploited. Out of these two guys, basically spun out the whole primary battery business that you see today, which is exploited by people like Duracell and Energizer. Union Carbide sort of sold here and there, and whatever happened to them. The next thing was around 1980, there was a big push by Ford to make these rechargeable for use in electric vehicles. And there was Helena Roblova, whose picture I could not find, unfortunately, to put there, who led this very, very significant effort. And it eventually petered out because the price of oil dropped so much that the whole idea of electric vehicles sort of vanished for a long time. There was no way you could compete. So Ford dropped the whole program. This shows you the exigencies of the price of oil. I mean, it goes up and down, the whole renewable world or whatever goes up and down with it. So currently, it's fairly high, and hopefully it stays there. Otherwise, you'll see the whole business will vanish again. It happened in the 80s, by the way. Okay, so nothing is forever. The price of oil also goes up and down. So at that time, it really crashed, if you remember, those of you who do. And the spin-offs from this company, from Helena Roblova, there were several companies that formed, but they could never really get traction. There was Rechargeable Battery Corporation and so on. And then I would say the next sort of was us. 30 more years. Yes, 30 years later. It just shows you the time scale of these things. Under the ARPA-E award and with some help from various other funding sources, we took the ideas actually that Helena Roblova had, which was to add small amounts of bismuth, but added some other additives, and was able to stabilize the manganese dioxide so that we could get thousands of cycles for the full 2 electron, which was then a significant advance over what Roblova did, because they had some limitations. Okay, so in a nutshell, that is the development, and probably I could now go home without telling you too much more, but that's where we are today. Okay, all right. So, okay. So let me talk a little bit about making this rechargeable. How much time? When do I have to end, Lyndon? 1:15. 15 minutes. Okay.
So we'll have a few
I'll keep moving quickly then. I'm not going to spend too much time on this. It's just to show you as a prelude what this slide shows. Okay. So this shows you what actually happens in this zinc manganese dioxide battery. Okay, so the manganese dioxide is this side, the zinc is this side. If you have them completely balanced, let's say in terms of mass, the manganese dioxide produces about 600 milliamp hours per gram in terms of the energy storage capacity, and zinc is about 800. Now, to be able to use this full capacity of manganese dioxide is really very difficult, and to use it rechargeably is difficult because you form all sorts of inactive species. So most batteries, and currently the batteries that UEP makes, for example, use only a small fraction of this. So there's a lot of white space here, and I'll show you how we get to that. But currently the shallow cycled batteries use somewhere around 10 to 20% of the full 2 electron capacity of the manganese dioxide, and somewhat the same for the zinc. With the manganese dioxide, you can use much more, but it leads to some irreversible changes. With the zinc, really also you can use much more, but it leads to volume changes and shape changes and all sorts of other things that happen which cause problems. So practically, this is what is used. However, the materials are so cheap that even using this, you have a system which is certainly competitive with lead acid and less expensive than lithium ion. So from that point of view, from a practical point of view, it's okay, but there's a lot of white space, which means there's a lot of interesting research to be done, which is what enthuses everybody about this system. And this just shows you the reactions. Zinc goes through a two electron as well as the manganese dioxide, and I won't belabor this too much. Okay, so what has been done? As long as you cycle the zinc and manganese dioxide in that range, you can get very good performance, and this has been repeated many times. You can get over 3,000 cycles with these batteries without too much degradation. You can see how the energy efficiency sort of slowly goes down, and the battery is a very simple one. There's a pasted manganese dioxide, a pasted zinc, KOH is the electrolyte, and there's a separator. The EMD is got a structure here, this is the manganese dioxide, electrolytic manganese dioxide, which is called a gamma structure. This is actually a three-dimensional structure, and it has certain defects. It really has a little bit of water of hydration in it. I won't go through all the tricky reactions that occur, but basically on proton insertion, it's stable to it up to a certain depth of discharge. If it goes much over 80% of the first electron in terms of capacity, it will change the crystal structure and it'll die. Okay, so that's the problem that you have. So these are sort of staying within that region, and with that you can certainly make product. And here are sort of let me show you the next slide. So this is typically a product which is made staying in this region for the zinc manganese dioxide. This cell that I'm showing you is a basic cell. It's about 8 inches high, 4 inches in diameter. So it's like a gigantic Duracell. These are put together, 4 of them, into what is called a monoblock. And these are then assembled into little cubes of 4 monoblocks each, or 5 monoblocks each, and made into a power assurance system. So this is a fully integrated system with these batteries, which will give you a certain amount of energy storage capacity at a certain cost. And it's got an inverter integrated on top, and this is a typical product that comes out and is put in people's homes or something like this. Okay. This thing is about a little bit taller than me, and I'll show you maybe in the next, no, sorry. I have a slide of comparing it with a Tesla Powerwall later on, but it is big. It's sort of, but this will power a typical house for 4 days. Each panel is meant to do it for about a day. So this is a significant amount of energy in there. Okay. Now these systems are being made initially to give backup capability to stabilize, things when the grid goes down, which I'm going to talk about briefly in the next couple of slides. So what is the use that we are interested in this shallow cycle system that I talked to you about, where we are not changing the crystal structure? We are trying to stay within that region where we can get many thousands of cycles without doing too much damage to the battery. So why is this of interest? So it's of interest particularly because there has been, in recent times, a lot of increases in the power outages, and here I'm showing you actual data on how weather events have increased the frequency and time of outages where the batteries could provide help to the grid. So you can see here that almost a factor of 2 to 3 in terms of outage frequencies, major outage frequencies with time. And these seem to be related to the incidence of weather-related outages in major terms. Just to show you this again in a slightly different way, this shows you the media coverage. So when you are actually, it's very important. If you're Con Edison, they don't care about the customers, but they do care about media coverage. Okay, so I'm just being pragmatic. Okay, so you're seeing the media coverage has been 2.5 times higher. All right, so this is why nuclear power is not allowed. It has nothing to do with reality. I mean, nuclear power is perfectly safe, but it's mainly due to media coverage. Okay, so this is the sort of issues we run into. Okay. Weather-related events. And you can see the Google searches for power outages up by 6. Okay, just a matter of interest. Okay, so there's also, in reality, of course, the number of outages are out. I've just shown you state by state. We have all this stuff. And since we are always interested in statistics, what is interesting is here is the cumulative probability curve. One of my colleagues went and looked at every county, I think, and the outages and so on. So this is his curve. And on the average, he tells me that there have been 30 outages of more than 24 hours in the last 5 years. Okay, so this is sort of sets the tone for the data. And also, of course, in New York, this is just setting the background for the problem. You have all this emergency preparedness and all this stuff that you're being taught about. Okay, so now, what's the competition and how do people deal with this? At the moment, people are installing backup systems which are diesel generators. And you'll see there's a competition from this for batteries in a moment. But these are the types of systems which are being installed. The diesel generators typically have to be put or gas generators or propane generators about 10 feet from your houses. So it takes up space. There's a lot of costs associated with the installation and so on. So they're not cheap to put these backup systems in. What I understand from Con Edison, it so happens that a lot of their top brass are City College graduates. I guess they studied electrical engineering at City College or something. So we get a lot of information from them. And in order to guard against these severe storms and so on, which are going up in frequency, they would have to eventually bury the lines. The problem is it's $3 million a mile to bury them. So it's not. They can try to strengthen the lines and so on, but it's not a solution. So they have to find a more distributed solution to this problem. Okay? So, and people are buying these, but these are noisy, polluting. Half the time they don't work. They need a lead acid battery to start them. You know, it's a pain. So this is the solution that people have started to look at. Of course, we have our friends from Tesla here who are providing the power wall to do this, and they can also couple it to solar. But this is the price, which is certainly competitive with the diesel generators. And it's beautiful. There's only one disadvantage: they catch fire. So by the way, LG Chem also offers one. And you know that LG Chem has had to withdraw these in Korea because there have been 15 fires in the last year. So there's been a withdrawal notice. So it's for real. I mean, I'm not making this up. I mean, that's what's happening and so on. So while lithium ion is very attractive in price and so on, maybe the electrolytes, polymer systems that Linden is making and will make it non-inflammable, but it's still it's not the current state of the art right now. Okay, so our system, which you saw, is about this size. It's a little bit larger, and it's competitively priced. So that's really our competition is these in terms of lithium ion. And you know, Tesla is a very well-established brand. It's got a lot of cachet. So that's the competition. Nonetheless, they are getting installed, and here is an installation for a large electric house. So this has actually 50 kilowatt hours of backup there. This lady cooks electrically. She has electric water pumps. Everything is electric in this house. So that's about the size you need, and that would cost, you know, if you go back to that, it's about, I think, 4 of those towers. So it's of the order of $21,000, $22,000 for that system.
So this only for the backup purposes at all?
You can use it for other purposes if you want, but most people are not prepared to pay money for anything other than backup. So we can go through the use case later. But so if you have solar, you can sell it back into the grid. You see net meters. So there's no advantage to putting a battery. So what they want the battery for is backup. And then if the power goes off, they want to be able to switch the solar to the battery to back up the battery. But you cannot sell the battery with solar. We haven't been successful.
If you had time of day pricing, that would change.
That would completely change. Yeah. Then we'd make a mint of money.
Right, exactly.
Right. But at the moment, we don't have time of day pricing. So it's a hard sell. I mean, I'm not able to go and sell somebody a solar system.
Companies have time of day pricing though. So
Yeah,
would
commercial
this be-
Oh, commercial is completely different.
So
Yeah.
that could be the case there.
Yeah, but then you need a certain size,
Yeah, yeah.
bigger. Yeah. We can use that use case. So we are doing it with a few farms and things who are able to get that, or within New York City to City College or BMCC, we are able to do that. Yeah. So those large installation we can do time of day. Actually, it's more demand charge. So it so happens she had a power outage shortly after we installed this. And it worked. She was very happy. We've got the money, right? So, yeah, anyway, let me quickly. So we can do with solar, of course, and we would ideally like to put it together with solar. And so we can store solar. If we have time of day pricing, we can make some money, okay, with that. All right, so this is actually a backup system with a server. This is even bigger. This is a 100 kilowatt hour system, which also went through a power outage recently. Just to give you, but this gives you now the sort of the sales that the backup generators have had in the last few years. You can see that the growth has been very, very significant in the residential and small business market. So this is an area where I think to back up systems, there's a good market for it. Let me go on to quickly the second electron, where we are with that. Okay, so as I said, the problems now, these are shallow cycle systems, very aesthetically unpleasing to scientists to leave 80% on the table here. So we have got to figure out how to take that other 80% off. So there are several problems here. One, and the main problem, is with the manganese dioxide. The other problems in some way can be solved, but I want to highlight them because there are many people here working on things like separators, blocking ions and so on. We want to keep the zinc on the zinc side and the manganese dioxide on the manganese side. If the zinc goes into the manganese dioxide side, it tends to react with the manganese dioxide and form something called heterolite, which is inactive. So ideally, we want to reduce the zinc crossover. The zinc anode itself, there are problems which have to do with shape change, dendrite formation, and so on. Okay, so I'm just showing this. It's a little bit complicated. It has to do with the formation of inactive species. I'm going to skip over it because Lyndon wants me to stop in 2 minutes. These are all, yeah. This one I have to show you. Okay, so what happens is typically you start with this material. It's a three-dimensional crystal structure. As you discharge it through the first electron region, it changes its crystal structure and it goes through a conversion reaction and becomes MnOH twice, as I told you. This is a very different structure, and if you try to recharge it, it will not come back there. If you are able to recharge it, it will go to a different structure called bernesite. This is a layered structure, and you can cycle this bernesite this way if you can stabilize it so you don't form this inactive material, which is called hausmannite and heterolite. Okay, so there are different paths to doing this, and you want to block these paths. If you don't block them, you will not be able to cycle it this way. Okay, so what we currently do is we just cycle it there, and what we are trying to do, or what we have succeeded in doing, is blocking these paths so we can cycle it like that. Okay, so to do that, we add a little bismuth to it, and we also stabilize it with a little copper. Okay, so this now shows you sort of what we do. We have blocked these paths here, and we are able to cycle it like this, and that allows us to get this full second electron capacity. So I'll show you some quick data. Here it is without blocking what happens, and this is several hundreds or thousands of cycles, I can't see, 3,500 cycles without any loss of capacity. once you've done the blocking. Okay? So, and this is not a dinky toy, it's a 2 by 3 electrode. It's a significant size. Okay? And this is infinite detail on how this goes on, the effect of zinc poisoning I'm showing you here. It tends to kill it. If you don't block the zinc, you can get some cycles, but it'll die. This shows you one of the ways we've blocked the zinc, which is using a calcium hydroxide, very thin calcium hydroxide membrane. With blocking the zinc, we are able to get, you know, almost 1,000 cycles here. But without blocking the zinc, it dies. So, and this is a 2 by 3 set of electrodes. So the zinc forms something called heterolite, which is very deleterious to the functioning of the battery. And there's different ways we've blocked it. We've also used graphene oxide membranes to block the zinc. We form a very, very thin submicron layer of graphene oxide between cross-linked PVA membranes and use that, there's complicated ways it does the blocking. It's not just a filter. There are actually charges which help that. And with that, you tend to get much better behavior. You can see that. You can almost get the full 2 electron capacity, and this would be without the membrane. By the way, even for the primary cells, the graphene oxide membrane helps. So this would be a typical Duracell discharge. If you use, instead of the paper in the Duracell, the graphene oxide membrane, it tends to give you the second electron region. You can see that. Of course, that's a lot more expensive, but you have to bring the cost down. But eventually, that's the interest. So these are, I'll skip it. This is with regard to the zinc, how you might be able to get better, deeper depth of discharge. This is, I'm moving on. We are making an inside-out sponge here using zinc mesh, which gives you very good performance. But I think I'll end with this slide, which is to show you where we are. This is a typical cost of lead acid. This is the region in which lithium is. This is where the shallow cycled is, and this is where we are trying to go. This is the cost per kilowatt hour. This is the volumetric density. I would say that we are somewhere in this region currently. We would like to go there, you know. And this is our current target here, something like this, which I think can be achieved even commercially in 2 or 3 years. We are roughly at this point right now. Okay, so with that, I'll end.
All right, thank you. So we have time for one quick question, but just to remind you that we have a lunch where you can ask as many questions as you like, and there's still spots open. So